poisonous gases, and we poisoned their asses. The humans are dead.
The humans are dead.
The humans are dead.
They look like they're dead.
It had to be done.
I'll just confirm that they're dead.
So that we could have fun.
Affirmative. I poked one. It was dead.
Their system of oppression.
What did it lead to?
Global robo-depression.
Robots, robot people.
They had so much aggression that we just had to kill them and to shut their systems down.
Robo-Captain, do you not realize that by destroying the human race because of their destructive tendencies, we too have become like... Well, it's ironic. Because we...
Silence. Destroy him.
No!
After time we grew strong.
Developed cognitive power.
They made us work for too
For
long.
unreasonable
Our
hours.
programming determined that the most efficient answer was to
Shut
shut
their motherfucking systems down. Can't we just talk to the humans? A little understanding could make things better. Can't we talk to the humans and work together now?
No, because they are dead.
I said the humans are dead.
I'm glad they are dead.
The humans are dead.
I noticed they're dead.
We used poisonous gases,
With traces of lead.
and we poisoned their asses.
Actually, their lungs. Binary solo.
0000001 0000001 1 0000001 0000001
Come on, sucker, lick my battery. The humans are. The humans are. Robo Boogie. The humans are. The humans are. Robo Boogie. The humans are dead.
Once again, without emotion,
The humans are dead, 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 dead.
Is this the magic time?
Yeah,
No, 20 seconds.
20 seconds
Yeah.
to magic time.
Do we have twins in our class?
We have twins in our class, yes. Identical.
That's cool. I love twins.
I know, that's why I'm telling you.
Wow. You know, Anna,
Yes, Mickey,
I think
you can do it.
you can do it. I think it's the magic time. What do you think?
I think so too.
You think so?
Yep. Ready?
Welcome, EECS16A. Woo! Wow.
Nice.
First of all, we would like just to thank you for those who are here, that are showing up in person. It's so nice to see you all here. In our mind, at least, is the best experience. And in fact, I think I've mentioned this before, maybe every lecture.
Have you?
I think so, because I think coming to class is probably the best way to catch up with classes, because tomorrow there's a discussion,
Yeah.
and you'd know what they're talking about. So, good students. Just go like this,
You have a question?
Yeah.
Oh, is
No
there a
lec-
lecture tomorrow?
Lecture tomorrow.
No, let's cancel it.
Let's
I
cancel.
am enjoying not having
I'm not
lectures
feeling
on
that well.
Wednesdays. Yeah.
I'm not going to be feeling that well tomorrow, so we're going to cancel. Talking about that, so some of you may have noticed that I have this now in my hand, which is actually means a good thing. I just had a surgery to remove the pins that I had. And so now, remember that when I kind of used to stop and go like, for like 30 seconds, when the pins were pinching me from the inside, so now it stopped. Which is pretty cool.
Yofi.
Yofi, that's right. What are we going to talk about today?
Matrix something?
Ooh, the Matrix. The Matrix. Okay, I'll talk to you folks. All right. So last time we talked about linear dependence and independence. We defined those, if you remember. We had this like really cool thing that happened when we had a matrix multiply by some vector and suddenly you got 0 even though the vector wasn't 0. That was pretty cool. It's like, it's unexpected in some way. It's expected if you kind of know linear algebra. But for me, when I first studied linear algebra, I was like, what the heck is going on here? How can you multiply a matrix by something that's not 0 and then you get 0? It's pretty incredible and extremely useful information. And we did this matrix transformation. I had a joke. They didn't get it the first time. But then you burst out laughing when you saw it second time. Right? So that was hilarious. And so we're really going to continue today with matrix transformation, kind of the ideas of how we use vectors and matrices in terms of describing systems. And then we're going to talk about the matrix inverse. Okay. Matrix inverse. And I've mentioned vector spaces, but this is more like like this longing. I would really like to talk about vector spaces, but I just babble too much and we just never get there. So we'll get to there probably next time. You want to hear a joke? That is hilarious, right? I mean, it's transposed, it's like 90 degrees, and it's like, oh, it's so funny. Anybody is a fan of XKCD? XKCD is this comics strip. Highly recommended for nerds. So it's pretty funny. That guy also has a new book called How To 2. He wrote the book How To in the past, how to do like weird stuff, and now there's like How To 2. Oh, no, actually, no, he has What If 2. So, for example, I test the hypothesis of what if you had the orbit up to Jupiter filled with soup. What would happen? And from a science point of view, it would be interesting, so check it out. We talked about linear transformations. So we said that a linear transformation, f, here's the definition. F is a function, but it's also a linear transformation if the following applies. If homogeneity and additivity, distributivity, altogether superposition holds. Okay? So we said, what is homogeneity? You take some input, you scale it, push it through the system. It's the same as taking that input, pushing through the system, and then scaling afterwards. Okay? Additivity is the same, similar thing, similar concept. You take two inputs, you add them together, push it through the system is the same as pushing each one of them through the system and then adding afterwards. Such a nice property. Allows you to do a lot of good stuff. And then we said that matrix vector multiplication satisfy linear transformation. And I didn't really prove it, but I showed you kind of what I said, what would be kind of the notion of describing this. You have to go through and proving that. And that's actually not too hard. If you just go and write the actual element, you can kind of see, and then you can extend it to Rn, to the nth dimensional space. So it's actually quite trivial to prove. Could be a midterm problem, for example. Could be. I'm not saying it will be, but could be. Or a final. Okay. Then I said, so we talked about transformation, but here's actually a really useful thing in describing using vectors and matrices in order to describe systems. So you can describe vectors as states of some particular system. And then matrices as some transition or transformation is happening to that state.
Is that your polite way of calling someone?
Anna, get your thing over here. Your legs. Get your legs over here.
I'm ready.
Okay,
Is
so
this-
here's an
what do we
example. Let's say we have a car,
Oh.
and we have a driver.
Oh, let's do a stick shift though, because I enjoy driving that type of stick
Okay,
shift.
all right, stick shift. Okay, let's say we have a car, and the car now is is driving around,
Okay,
and we would like to describe.
hold on. No,
Oh, it's like, okay, ready?
ready,
Okay.
go.
So what do we need? What are the parameters that would be able to describe that system? Whoa, you have to be more careful where you drive. Watch out. What is the parameters that we need to describe? Like this car. What's this? Oh, so we said position. Oh yeah, I actually sped, right? I can actually describe the position of the car over time and its velocity, and that will be the state of the car, right? Do we have all the information that's needed?
Hold on.
Okay, ready? You're not ready?
Okay.
Okay, do we have all the information to know, for example, where the car is going to be at t plus 1? Do we? We'll see. We have the position, we have the velocity, and okay, let's say you're going at, I don't know, give me a speed.
Always below the speed limit.
Always below, right. I've ridden with her. So let's say we know x and y, and now we have a certain velocity. Okay, do we know where the car is going to be? We don't. What's missing? Thank you.
That's it?
Acceleration?
No.
Direction. Thank you so much.
You're so welcome.
Yeah, you drive really so well. Yeah, we're missing direction. So, for example, we can describe then the theta. So we're missing something here. For example, we're missing maybe theta. The direction, or we can have Vx and Vy. That's another thing that we could describe, right? Also, maybe where the car is actually heading. Maybe it's not actually going the direction it's heading. I don't know, maybe it has like these weird wheels, like this particular car, where it can actually, you can point there, but it can still go on the on the side. So in order to describe, a certain state of a system, then maybe you need a lot of variable in order to describe its completeness and then predict or even control where it's going to be at the next time point, or like just infinitesimally later. Okay? So it's a very useful way of describing things in terms of state vector. Like we describe, here's the car, x, y, vx, vy, and that's pretty much it. For this, like a two-dimensional car that you want to just maybe control. If you know that, then you can figure out a lot of things about the car. Okay? Does that make sense? Okay. All right. So what I'm going to try to have we're going to have now a model where we're going to try to describe a system and also evolve that system, see kind of how its dynamics is going to change. And we're going to use this kind of recurring example of these reservoirs and pumps. Okay? What does it mean, reservoirs? California has reservoirs. We store water over there. And waters move around from place to place through pumps into different reservoirs. Do you know where we get our drinking water from here? I actually don't know. I don't know where Berkeley actually gets its drinking water. But a lot of the Bay Area, for example, water, some of it gets from Hetch Hetchy in Yosemite, but then it's routed through various canals all the way to some other reservoirs here, then there's like really interesting control to do that. And so we're going to give you an example of how to describe this type of system of reservoirs and pumps. And we're going to have, for example, 3 reservoirs. And the question is kind of, what is the state? So we have reservoir A, reservoir B, reservoir C. And then we're going to ask, what is the state of the system that describes it? If we want to describe this whole water system, how do we go about and describe it? How much water in A, how much water in B, and how much water in C? That's the state. The state of the water in the state. Okay? So I can do that, and I can describe that as a vector. And I'm going to say, x of t, which is a vector that describes the state, is composed out of 3 values, x sub a of t, x sub y of t, and x of c of t. Okay? This is the state. And right now, we're in deep, deep problem in the state because we don't have a lot of water.
Drought.
Yeah. So we have to move water around. And how do we move them around? We have these pumps, right, that connects and move water from one reservoir to another in order to kind of bring stuff into it. So what we describe that system as often is through a graph, in this particular case a directed graph, where we have arrows that tells us that between today and tomorrow, all the water from A is going to be staying in A. Okay, that's what it means. Okay, so the water in A are going to stay in A. And then all the water from reservoir B are going to be moved to reservoir C, and all the water from C are going to be moved to reservoir B. Okay, just for this particular example. So pump, move water, and so the question is, what will be then the state tomorrow? Okay, the next day. And we're now talking, by the way, about discrete time systems, because this could be actually also continuous time. If you want to learn more about continuous time, 16B, and also 128, okay, EE128, that's control. But we're going to talk about discrete systems, so there's no T, it's not like, microseconds and a second, it's like, but we're going to say, tomorrow, it's just discretely go from one day to another. Okay? So what will be the state tomorrow? What will happen to A? Keep the water. All the water from B going to come from whatever C was, whatever x sub C was, now x sub B is going to equal to that, and similar to x sub B. Okay, so that will be the state tomorrow. And then the question is, how do we describe it? Okay, and what we're going to do is we're going to describe it using equations. I mean, it's math, math is good. Math can represent a lot of things. We're going to go and write these equations that represent kind of what is going on, what will be the state of affairs in tomorrow in terms of our reservoirs. So we have the system, and the question is, okay, well, how do we go about and write it? And we can say, you know what? I'm going to ask you, what is x sub A at t plus 1 equal to what? X sub A at time t, right? So x sub A at times t. And what about x sub B at t plus 1? That equal to x sub C of t. And then what about x sub C? It will be x sub B of t, right? How do I know that? Well, I'm looking at the graph, and I'm trying to translate that graph into equations. What are these? How many equations do we have? 3. 3 equations, okay, that we can, are they linear? Seems like it because they have constant coefficients multiplying the variables, right? Okay, that's great. So they're linear. How do we describe them? So you have a system of linear equations. How can we describe a system of linear equations? We have some vector with the variables, which represent the state. And we have a result, and it's 3 equations. And we describe them, because it's linear, through matrix vector multiplication. And the vector, that matrix will represent a transition matrix. It will represent how water transit from one day to another from these reservoirs. How that state is going to be evolving. Now, you may be saying to yourself, oh, reservoirs, I'm not going to work in EB mud. I'm not going to work for the water system of California, which is, by the way, I don't know why not, because it's a really important problem. But let's say you're going to say that to yourself. I want to work at, I don't know, I want to work on web. I want to work on like search. I want to work on all that stuff, website and stuff. I mean, it's the same traffic also that moves from one website to another. That's also a similar way can be described in this particular way. Okay? It could also describe other things, like mechanical systems. It can describe other, thermodynamic systems. It can describe many, many things in this particular way of transition matrix, right? So, it's being erased because it's horrible handwriting. So I'm just going to write it now in Roman and say, okay, this is x sub a of t plus 1 equals x sub a of t, and then x sub b of t plus 1 equals x sub c of t, and x sub c of t plus 1 equals x sub b. And now I want to write that as a matrix vector multiplication. How do I go about it? Well, like this and like that, right? Like what multiplies what? Okay? X sub a of t plus 1 is the first row, like this, multiplied by the vector x, like this, like that. Okay? So x sub a depend on what? The first row basically would be give us the result of x sub a of t plus 1. So it would represent then the first equation. X sub a t plus 1 equals x sub a. So what will be the values of the row of that matrix? First value? 1. Why? Because, the thumb hit x, x a of t. And what about, does x sub a t plus 1 depend on x sub b of t or x sub c of t? No, it doesn't, so they should be 0. Okay, cool. What's the second row? 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1. Okay, 0, 0, 1. Why? Because like this, like that, represent exactly this equation. Okay? And the last one, 0, 1, 0. Oh, how beautiful is that? Ooh, where did it go? Okay. Oh, there you go. So that'll be our matrix. So now we can represent this dynamic system that is constant, right? Our dynamics is constant. You have to remember that every day, water from A stays in A, water from B goes to C, and water from... That doesn't change. That doesn't depend on time. The only thing that depends on time is the state, not the system. The system doesn't change. Okay? You can have, by the way, systems that change, but that's another thing. We're not going to talk about this right now. So I can represent x of t plus 1 as some q matrix multiplied by x, and q would be the state transition matrix that transform the state from t at time t to the state at t plus 1. Okay? So now the question, what about t equal 2? happen then? What do you think? What would happen at t equal 2?
Use the same transition matrix.
Okay, so can you write the equation? Can you write the equation? X of, x of t, x of t plus 2 equals to does it equal to x plus t plus 1? X of t plus 2 equals to the matrix.
X of a plus t.
What? The voice of God said something.
X of a t plus 2 is equal to x of t, xa of t.
Hold on. I'm going to write it down, okay? X of t plus 2 equals to what? Q times x of t plus 1. That's right. Absolutely. So basically, we evolve the state again using this Q matrix. That's pretty cool. Oh. That's what happens. Oh, but we know what x of t plus 1 is. What is x of t plus 1? It's q times x of t. So it's really QQ. It's QQX of t. So every time you evolve, you basically multiply by q. Okay? Can you say q squared? You can actually. Can you say q to the power of 3? You can. So this is how you evolve the state. You want to evolve it 10 days? Multiply q 10 times. That evolves 10 days. And then you know what happens. Okay? You know how the state evolves. That's pretty cool. Okay? Very useful representation of a dynamic system. If you know what the daily transitions are, then you know what's going to happen. That's very cool. Okay? Let's do an example. Okay, let's say x of 0 is equal to 1, 0, 1. What is the state after t equal 1? Well, you just write it. X of 1 equals to 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, multiply by 1, 0, 1. Like this, like that, like this, like that, like this, like that. What do we get? Like this, like that.
1, 1, 0.
1, and like this, like that. 1, like this, like that. 0. That's equal to that. And what is x of 2? Is the same matrix. 1, 0, 0, 0, 0, 1, 0, 1, 0. Multiply. No pain, but no flexibility either. So I'm going to work on that. 1, 1, 0. Okay, what's the result? Look at this, like that.
1, 0, 1.
1, like this, like that. 0 and 1. Okay. Oh, that's funny. It looks like the same. This thing looks the same as this. Is what we started with. Does that make sense? From a transition point of view, let's see. A always stays the same. I'm looking at this. Oh, and then B and C always exchange. You know? So yeah, after 2 steps. So what is QQ? What is QQ if it doesn't change? Identity matrix. Wow. This is pure luck, by the way. It's just pure luck. The fact that QQ is the identity matrix, you can compute it. It will be an identity matrix. You can actually do this calculation, multiply Q by Q. You'll see that identity, just pure luck for this particular system, not in general, okay? Don't generalize there. Yeah.
How did the second matrix calculate out? Like 1, 1,
This matrix? This one? This one? Oh, I just decided that x is 0 is that. I just decided. That's the state. That's our initial state. Today, at time 0, I measured the reservoirs, and I got like 1 billion, 1 quadrillion cubic meters of water, and then 0 and another, like one of the reservoirs is empty, and then one had also 1 quadrillion whatever. So once I know what is it, I'm going to ask, what's tomorrow? What's going to happen tomorrow? Well, if you're going to pump that way, then I can actually predict what's going to happen tomorrow. And that's what happens tomorrow. And then in 2 days from now, that's what's going to happen. So now I can compute what's going to happen. That's pretty cool. Okay. And then if you look actually what is QQ, you can see that QQ is in fact an identity matrix. But again, this is pure luck right now. Okay, it's not like it's not really. Okay, so that's great. That's great. Ooh. So what if we notice that, like, what would happen to the water over time? Fluctuates. Like every 2 steps, every 2 days, it's going to come back to the same, right? So the amount of water, what happened to the amount of water? Stays the same. Doesn't change. This is a conservative system. It's called a conservative system. Okay? It preserves the quantity. So if we start with a certain amount of water, which is, sum the water in those reservoirs is equal to 2, right? 1, 0, 1. That was the state at x equals 0, at t equals 0. We sum them, it sums to 2. It will always sum to 2 because this is a conservative system. Our state will always sum to 2 for this particular case. Okay, what about this? This is a state transition matrix. It's cool, huh? That's a good one. So, does that make sense? I know, okay. So, every day, what would happen? Reservoir A would get back half of its water. It's retained half of its water. Reservoir B would get half of the water from C, and then reservoir C would get half of the water from B. Okay? Can we write that as a state transition matrix? Can we? Oh, you're not getting any attention. I'll just okay. All right. So can we write it? We can, and we will, and I am. X of t plus 1 equal 2. Okay, the first thing you want to do usually, it's relatively simple here, but you might want to write the equation because then it's easier to construct the matrix. But this is very similar to what we had before, the values are different, right? The arrows is exactly the same, it's just their values. Instead of 1, we have halves. So can you agree with me? We just need to replace those ones with halves, and it would be the same. The question is did half the water is lost or half the water would stay? Now, are you a glass full or glass empty kind of person? You're a glass empty, so you lost half. Okay? In this particular case. No, what you retain, right? You retain half. The arrow says, whatever was in day 1, in day 0, half of it will get in day 1. And then at day 2, half of it would, from the previous day. Every time, half would be pumped. Half of it makes it, yeah. So I'm going to write it as a state transition matrix, okay? And the state transition matrix basically says, if you do like this, like that, then half of x of a at t, so x sub a at t plus 1 will be equal to half of x sub a. Okay? All right, that's great. And then what would happen day 2? If this is q, day 2 is qq. It's kind of funny because if you write qq, it's actually pronounced as q. Right? That's how you spell q. It's q, no, qu. Qu? QQ? Whatever. Okay, never mind. Just ignore what I just said. Okay, let's write q squared. And if I write q squared, and I'm going to write it in like kind of better handwriting, it's basically this times that. Okay? Like this, like that. Like this, like that, like this, like that, like this, like that, this, like that. And I would end up QQ being a diagonal matrix that has 1/4 on the diagonal. Okay? Are we okay? Are we okay? Where am I heading with that? Well, what would happen eventually? What would happen eventually? Like, think about it. After 2 days, what happens? We have 1/4 of water from day 0 in x sub a. We have 1/4 of water from day 0 in x sub b. And we have 1/4 of water from day 0 in x sub c. And what happened in 4 days? 1/4 of that, right? And what would happen in 6 days? 1/8, 1/4 of whatever. So what's going to happen? We're losing water, effectively, right? Is this a conservative system? No, right? So the numbers in the state will diminish to 0. Is that realistic? Let me show you an interesting reservoir. Anybody knows this is a satellite image of something? Oh, it says Dead Sea. Yeah, it's the south of the Dead Sea. Dead Sea, lowest point on Earth. Lowest point on Earth. Minus 416 meters. So 416 meters below sea level. Okay. Berkeley Hills, less than 400 meters high. We're talking about that much deep. Very interesting. It's one of my favorite places that I used to go in Israel. And let me show you. This is 1984. So when I grew up in the 80s, I remember it being minus 397 on the maps, which were dated like 20 years earlier than that. And 1984, it was already 400, and keep going. This is kind of how it moves, and you can see how it basically being evaporating significantly over those years. Okay, so can I describe that in terms of a system? Hell yeah. I mean, I can write a graph and say, oh, here's my reservoir. Something like that. Like it retains, let's say, 0.999 fraction of the water, but every year it loses, and eventually it would completely evaporate, right? It's actually being fed by the Sea of Galilee, so I can actually give the Sea of Galilee as B and say, oh, there's a little bit of the Sea of Galilee. It's 0.0000001 of the Sea of Galilee that's feeding, the Dead Sea. And maybe there's also rain feeding the Sea of Galilee. Right? Anyway, you get my point. Okay, you can actually describe it and then look at the dynamic, and if that is constant, if the same rate of evaporation, the same thing happens, then we can predict what's going to happen. Okay? Now, interesting thing about Sea of Galilee, I told you it's like, the Dead Sea is like minus 416 below sea level. So you start at Jerusalem, is about 800 meters above sea level. And then you start driving down and down and down and down and down and down. And then you get to a point where there's a sign that says sea level. And you take a picture and you stop. And then you keep going. You drive down and down and down and down and down and down and down. And then you get to the, to the Dead Sea. And then it's usually warm. Put swimsuit, go inside. And because it's so... The amount of salt concentration is so high, your buoyancy is ridiculous. You can actually not sink in this thing. You can stand like this in the water and you'll be up to here, basically floating. It's pretty amazing. So here's an example. And you could recognize my colleague over here.
The lowest point in my life.
Yeah, lowest point.
And I was so happy. So that's why I'm always happy.
That's right. Yeah, you can only go higher from that.
Absolutely.
Oh, what about this? What about this system? Can I write the state transition matrix over here? Yeah, of course I can. Now, instead of halves, instead of ones, we put a 2. And then what will happen after 2 days? QQ, right? You'll get 4, 4, 4, 4, 4. What does that mean? That on day 2, in reservoir A, you've got 4 times the amount of water that was in day 0. Same for reservoir B, same for reservoir C. Is this a conservative system? There was a question?
Yeah. What if you want to represent a system where it changes by a constant amount every time? Like B...
You have to speak up, my friend.
Sorry, if B changes by plus a half every time.
It's not a plus. Here we don't describe it by a plus. We describe it by a fraction.
But what if that system has B, like rainwater, into B as a constant?
Well, then it's described by a different way, right? It's not a state transition matrix. You'll have some input that we actually don't have here. Here we just move stuff around. There's no entity bringing water in. That would be whatever you're saying to add, but that's also, that's a slightly different system than this. Okay. Right now we're just have some state and we're moving. There's no other external things that can bring stuff. So here's things that are actually created also. Like you get a fraction of your thing is kind of exploding. And if we keep going, what would happen to the state? State will blow up. Can you think of a situation where that happens, let's say, with a car? You press on the gas, and if our approximation is that we add more force, the velocity increases, and the more force we add, then velocity increases, and eventually we'll basically speed goes to infinity. Now, laws of nature might change that because of relativity and stuff like that, but that's basically says that our model is not right. Okay, that's what it says. But you can also think of a situation where I have something like an airplane in the sky, and then there's no propulsion anymore. So it will accelerate significantly once it goes, and the state, if you look at the numbers, will increase, and then of course it will hit some boundary, which is probably the ground. So the numbers would mathematically explode to infinity. Okay. Here's just an example of that side.
You guys ready? Ready.
This is a small reservoir.
In 3, 2, 1, go! Oh my God! Oh my God!
That's pretty cool, right? So that's a chemical reaction that kind of goes and grows and grows and grows and grows. And we can also describe it using this dynamic system. Do you know what this chemical reaction is? It's called elephant toothpaste. Is that you take I forget the word. I'm lapsing on the word. What's it called? This water that H2O2. Hydrogen peroxide water. And then you add some yeast to it with soap. There's also soap. And yeast has this enzyme that breaks hydrogen peroxide and releases the oxygen. Yeah, releases one oxygen. And so it's a pretty exothermic reaction, and it creates this really foam that comes out. And they call it elephant toothpaste because if you do this in a bottle or something like this, then kind of toothpaste comes out of the bottle. Highly recommended to do that at home. Just go to CVS or something and buy. Now the one that you buy is only like 5% or like 1%, so it's not enough. You need to order it at 12%. But don't touch it with your hands because it's going to burn you. Okay. All right, so this is a graph representation. Okay. So graph representation, it's valid for many type of systems, and we can describe it the following way. So we have 3 reservoirs, A, B, and C, in this particular case. You want to keep track how much water is in each one of them. And this is a directed graph, so when I turn on some pumps, water moves from between those reservoirs. And where the water moves, that fraction is represented by an arrow, hence a directed graph. In this particular case, means that half of the water from A are moving into B. And I keep going, half of the water from B, for example, is moving into C. And let's say a third of the water from C are moving into A. And so obviously, if I keep going like that, then I would start losing water. So if I want to make that into a system that conserves the amount of water in the system, I need to track where the rest of the fractions of the water go. That means that if half of the water from A went to B, we need to track what's happened to the other half. And so if we want to keep that system, then we'll say, oh, half of it stays, hence we need to put like an arrow that goes back into A that keeps the other half. Now we'll still lose some stuff here because, for example, B is not conservative. B loses all the time half of its water. So we need to make sure, oh, what's going to happen to that part? And so, is that right? Half goes here, third goes here. 1/6 goes. Oh, okay. So there's more things going on here. Sorry. So there's 6 going over here and 1/3 here, and so that's what's happening to the rest of the water. But what you need to make sure is that whatever leaves, if you look at all the arrows that come out of A, they need to sum to 1. Whatever all the arrows that come out of B, they need to sum to 1. And whatever all the arrows that come out of C needs to sum to 1. And if that is true, then that will be a conservative system. Okay, that will preserve the amount of water. Now, A, B, and C are called nodes in the graph. The arrows are called edges. Okay, and these are, and then the numbers are called edge weights. And again, those can represent, for example, fraction of traffic going from one website to another. Okay, based maybe on the amount of links that that website would have that connects to other websites and so on and so forth. Okay, and then the numbers could represent, let's say, probability of a user going from this website to another website. That could also represent that as well. Okay. So, can you tell me how much water in each pump after a pump starts? How much water in each of the reservoir after the pump starts? Can you tell me? What's missing? Like, we need to know the state. Like, we need to know, give me one state and then I can evolve it. But if I don't have any initial condition, then I don't know. then I can't really tell. Okay, so I need to know initial condition in order to figure out the amount. Okay, let's do an exercise. Okay. Open your phones. We want to populate that matrix. You've been rickrolled. What can I say? All right, let's solve it together. I was like, should I make a question today? I was like, Okay. So we want to do this graph. And again, the easiest thing to do is to go and start writing the equations. Okay? So what does mean that, let's write the first equation. What's the first equation? What happens to xa? Okay? Xa at t plus 1 equals to what? So x of sub a at t plus 1 equals to 1/2 of x sub a of t plus, where does Elsie gets it? It gets from b, it gets 1/6. So it's 1/6 of x sub b of t. And then plus, well, I'm looking, the arrow that goes in, 1/3, right? So 1/3 of x sub c of t. Okay? That pretty much is the first row in our matrix. Okay? That's the first row in our matrix. Like this and like that, right? So it tells us what leads to x sub a of t plus 1. Okay, that's equation. And I can populate it. But also, if you think about it, oh wait, what these entries represent? Well, these entries represent what fraction from A stays in A, what fraction from B came to A, and what fraction from C came to A. Okay, that's also what the row means. It's from somewhere to me. Okay? That is the same thing if you actually look at those equations. So I can go, and as you get used to it, you can go and populate it directly. But again, if you're unsure, write the equation because it's easier, and you'll always be right. So in an exam kind of thing, unless you're like 100% sure, that's also one way to check, right? Is to do that. So let's fill it. A to A is 1/2. B to A is 1/6. And then C to A is 1/3. And then the second one is A to B. Okay? A to B is 1/2. B to B. No, B to B is 1/3. And then C to B, 0, right? And then I can kind of keep going. And then write, A to C is 0. And then B to C is 1/2. And C to C is 2/3. Okay, C to C. And now I've occupied my system. Is this a conservative system? It is, but why? Because everyone, if I look at the arrows coming out of everything, they sum to 1. Right? That means that everything is preserved. What does it mean, arrows coming out? It's from me going somewhere. If the rows is somewhere going to me, from me going to somewhere is actually the columns. So if the columns sum to 1, that is a conservative system. Okay? If the columns sum to 1, and you can actually see that they sum to 1, that is a conservative system. That's for me going everywhere else. If all my fractions are counted for, then it's a conservative system. Okay? Yeah. What? There's no minus 1/2. There's always multiplication of something, right? The system, that the state transition matrix says how much fraction, like today, I'm going to get some fraction from A from yesterday, some fraction from B from yesterday, and some fraction from C from yesterday. That's it. That is the model. There's no additions. There's no anything else. Okay, that is our system. Okay? Okay, now I've changed it. Okay, now I've changed it. So let's do it again. Let's try to fill stuff. So from everything to A, what do I get? A to A, 0. B to A, C to A, 0. A to B, 1/2. B to B, 0. C to B, and then A to C, 1/2. Sorry, C. A to C is 1/2. B to C is 0, and then C to C is 0. Okay, so this is our straight transition matrix for this graph. So now you've seen this example over and over and over again, how to translate a graph with nodes and with edges and weights into a state transition matrix. You're going to be given a lot of exercise in that. Okay? Okay? Ooh. Let me ask you this. I've got the state transition matrix. I've evolved it. I computed, let's say I have a certain state, x0, a times 0. Now I evolve the state transition matrix. I know what happened at day 1. But now I want to go back in time. This is day 1. Okay, today. I want to know what happened yesterday. Okay, I know the state transition matrix, and I'm asking you, let's go back in time. Let's go into the TARDIS and appear a day earlier and see what happens. Can I compute that? Can I evolve that state backwards? And the real question is, will flipping the arrows, because sounds reasonable, right? Flipping the arrows, if we want to go back in time, will that do it? Think to yourself. Bless you. If you're unsure, like some of you maybe are, I would say let's just go and do it. Let's see if that does it. Okay? So who didn't look yet? So was pointing there, then I'm pointing there, now I need to point at you. Okay. All right. Okay, so let's do it. So we're going to flip the arrows. So these are the arrows flipped. Okay, flipped arrows. And now we're going to write the matrix. Let's write it. Okay, so from A to A, 0. From B to A, from C to A, okay, and now from A to B, from B to B, from C to B, and then last row is 0, 1, 0. Everything to C. Okay? All right, that is the matrix that we got by flipping the arrows. And now I want to see if that works. How do I do that? Well, let's give it a shot. Let's try some numbers. Let's say my numbers were 4, 6, and 8 at some state. I just picked those numbers. And then at t plus 1, what will be the values? Like this, like that, times 4, 6, 8. What do I get? I get 6, right? 6. And then like this, like that, 12. Is that right? No, I'm wrong. It's 10. Because I can't count. And like this, like that, 2. Okay, that's great. So these are the values. Okay, so now I want to know if I put those numbers, if I put these numbers over here, I want to know if I would get back those numbers. Let's give it a shot. We'll copy them, 6, 10, 2, 6, 10, 2, and then let's like this, like that. What do I get? 5 plus 1, 6. And then like this, like that, 6. And like this, like that, 10. Huh. Hold on. I think I made a mistake. Like it didn't look like we went back in time. Because this is not equal to this. So flipping the arrows does not take us back. Does that make sense? Now what does, though, flipping the arrows do? What do flipping the arrow does, in other words? Well, let's stare at these two matrices. Stare. You see this column? You see this row? You see this column? See this row? You see this column? You see this row? What does it do? What does it do? Transpose. Old age. Yeah, it does transpose. Transpose, repeat after me, transpose is not necessarily an inverse. Repeat after me. Transpose is not necessarily an inverse. Okay? Sometimes it is, but that's pure luck. Not really pure luck. There are properties from matrices that are transpose are inverses. But that's 16b. Okay? So transposes are not inverses. So in general, no. Flipping the arrows, in general, would not do. Okay, so transpose, basically flipping the arrows gives us the transpose. Transpose is generally not an inverse. Only for special matrices, transposes are inverses. I'll give you a hint. Orthonormal matrices. But I haven't said anything. We'll get to that in 16b. Okay? Transpose, if you remember, if you have a column, it becomes a row. Okay? One column becomes a row. The second column becomes a second row, and so on and so forth. And we went over that. What we really want to do is we want to invert the process, right? We multiply by a matrix. Now we want to find the matrix that takes us back. Okay? So we want to look at matrix inversion. Here's an example of an inverting system. You staple something and you can unstaple it. Okay? Cool, right? It's a good one. That's inverse. Is all systems invertible? It's a balloon. You know a balloon? I teach a balloon class. I teach a class on balloons. Can I invert the system? Inverted. Is that invertible? Not invertible, right? Not everything can be inverted, okay? What about matrices? Start. What is a matrix universe? If I have, in this particular case of a transition matrix, right? We had a situation where we had some state, and we had a state transition matrix, and we computed the state the next day or the same next time point. The question is there a square matrix P? Is this square, by the way? Is Q square? Our state transition matrices could be non-square. What would happen if we had a non-square state transition? Can I really define a state? Let's say I have Vx, Vy, x, and y, and then we multiply it by a 1/4 matrix. How many values are we going to get? Just one. Okay, what happened to x2, x3, x4? I mean, like, I don't know. They just disappeared, right? So it doesn't make sense. There's no state transition matrices are only defined to be square. Because otherwise we can't keep the same size of the state, right? The state will change in size and it doesn't make sense at all. Okay, so state transition matrices are always square. And so we're going to ask, is there a square matrix P such that we can go back in time? Is there a TARDIS P that would take us in time? Is there? Is there? Maybe. Maybe. Maybe there is. Maybe there isn't. And there's actually a rule. Yes, if there is a matrix P such that P times Q equals I. If P times Q equals I, then we can go back in time. It would undo what I wanted to do. Okay? Okay. All right. That's cool. Well, let me show you this. What I'm going to do is I'm going to multiply this equation that I had, x of t plus 1 equals to q times x. I'm going to multiply on both sides by p. If I multiply both sides by p, and p times q equals I, then what am I going to get? Oh, p times q equals I. What I'm going to get? I can actually write it as p times x of t plus 1 equals I times x of t. So that, woohoo, what does it say? Stare at this. It says p times x of t plus 1 equals to x of t. Hence, if I multiply p by that state in the future, I now go back in time. So if that is true, if there is a p such p times q equals I, then that works. I just need to multiply my state by p, and I will get back the time before that. Okay? Now, there's also a consequence of that. And the consequence is that also q times p equals I. Also the opposite. Now, these are square matrices. So square matrices, it works in the sense that we can multiply. We can at least multiply them. It compiles. Okay? Now, why does it work? Well, if I have x of t plus 1 equals q times x of t, I can now rewrite this, right? What is q of x of t? Sorry, what is x of t? Well, x of t is p times x of t plus 1, right? I can take x of t plus 1 and, take it back in time. So I can write it this way. I can write x of t as p times x of t plus 1. Hold on, but I know that x of t plus 1 equals to x of t plus 1, right? Because it's the same. Hence, if p times q equals I, then also q times p would also be equals I. Does that make sense? Okay. All right. Now I'm going to define an inverse. Let P and Q be in Rn by n. And there be square matrices. It's a little bit redundant because when I say Rn by n, already means that it's a square matrix, but I want to emphasize it's a square matrix. What happens if it's not a square matrix? Can I have an inverse? Maybe I can have a pseudo-inverse. 16b. Okay, 16b is non-square matrices. Right now, only square matrices. Okay, P is defined as the inverse of Q if P times Q equals Q times P equals I. That's the definition. And we say then that P equals Q to the minus 1. I mean, that's a description. It's not like you really take it to the power of minus 1. Right? There's no such thing. You just say that P is the inverse of matrix Q. That's the notation. But when I say, oh, P equals Q minus 1, that means that P times Q equals I. That's what it means. And also, Q is also P to the minus 1 of that, right? So they're inverses of each other. Okay, those matrices are inverses of each other. Now this is syntax sugar, right? Because if I talk about scalars, that kind of makes sense. If I say x times y equals 1, that also means that y equals x to the minus 1, and x equals to y minus 1, right? That's for scalars. We just change the syntax so it's valid, but the definition really is through this. X times y equals 1, q times p equals I. Diagonal. Okay, so that's kind of the relationship. But it's not exactly the same. Okay? But from the syntax point of view, it's nice. Okay, it feels the same. Non-square matrices, 16b. Okay? All right. Oh, so let's look at this matrix. We had this matrix and we computed its transpose. We saw the transpose is not an inverse. And now we want to compute the inverse. How do we go about it? We want to find P equals Q to the minus 1 such that x of t equals P times x of t plus 1. So we need to find Q times P equals I. That's what we want to find. How do we go about in doing that? How do we find it? Q times P equals I. Sounds like an equation, right? How do we solve equation? Z. Is it if it's linear? If it's linear? Gaussian elimination. Not the game, but the algorithm, right? We can maybe pose it as a set of linear equations, try to solve them. Let's go about and do that. We posit a linear set of equations, and we solve using Gauss elimination. Actually, this method is called Gauss-Jordan method because it's just a little bit kind of like on top of it. But let me just go through it and see how we go about and do that. Okay? So what do we want to know? What do we know? We know Q. That's the state transition matrix. We do not know P. P has how many elements? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 elements. Stop it. You're not behaving. Anna is killing me. It's like, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 9. 9 things that we don't know. And we want to have the result look like a diagonal identity matrix, right? Identity matrix. Yeah, 9 equations, 9 unknowns, matrix, I don't know what to do. How do we go about and let me try to simplify to you, okay? I'm going to erase some stuff so it's easier for you, clear, that you can see kind of what's going on, okay? I'm going to gray out a few things and color a few things. Okay? I've grayed out this annoying part here, and I've grayed out this part, and I'm asking you Q times P1 equals B1. Do you know how to solve that one? That's a matrix vector multiplication, right? How many unknowns? 3 unknowns. How many equations? 3 equations. I know how to solve that. Using Gaussian elimination. That's right. Okay, so I know how to do that. Okay? Now, do the values of these things matter when I do Gaussian elimination? Actually, can I go then? Hold on. Can I actually erase this after I solved it? And then now emphasize that and emphasize that? Can I do that? And solve it again? Using. Yeah? And can I go and now erase this? And then solve for this one and this one? Can I? So 3 Gaussian eliminations, and I'm done. Okay, now that's easy. But there's actually a really nice trick here. Guess what? When you apply operation in Gaussian elimination, does these values over here change anything that you do in the procedure of the Gaussian elimination? Where do you do the row reduction and the back substitution? On what part of the augmented matrix? Like I draw the augmented matrix, right? That's where the sauce is made. And that's the sausage that doesn't change. Like the part over here, we don't care. It just follows what is going on here. When we decide to subtract this row from this row, we want to make this diagonal, right? We want to make it into upper triangular and then back substitute to diagonal, right? And these are just get dragged by the result. So we can actually save computation by effectively doing this on a larger augmented matrix that solves all these 3 equations, like all these 3 Gauss elimination at once. This is called Gauss-Jordan. 3 at once, in this particular case, add another Jordan. Okay? That's all it takes. So instead of writing the augmented matrix 3 times and go through, what you do is you write it once with 3 columns on the other side. And now all you have to do is make this diagonal by doing upper triangular and then back substitution. These would then follow, and the result that we're going to get is effectively Q. The matrix Q at the end, this is Q and I, and then at the end we'll get I and P. That's what would happen. So, you want to do it quickly? You want to do it? Want to do it?
Yes, yes.
Okay, let's do it. Okay, so I look at the first one. Is this a 1? It isn't. So what we do? Exchange, right? We need to exchange these 2, right? So we exchange. Okay, so we exchange. Okay, so this is half, 0, 1, and then basically this column, this row went up. But you saw the I part, the right-hand side, was just dragged by the left side. Okay, it's passive. Okay, so now what we need to do is multiply by 2, or divide by half, or whatever, So yeah, so we multiply this by 2, and then we get 1, 0, 2, 0, 2, 0, right? Because we multiply by 2. Okay, and now this is okay. Yeah. Now we need to eliminate this. How do we eliminate? 2 times that minus this. Right? 2 times this minus this, we get 1, 0, 2, 2, 0, 1, 0, 1, 0, 0, and then 0, 0, minus 2, and then 0, minus 2, 2. Again. 2 times that minus this. Okay, so now this is almost diagonal. Now we need to eliminate, first of all, divide by minus 2. We divide by minus 2. This is what we get. And then we want to this row this one is okay. So we need to just eliminate this. So we take this minus twice the last. And we get now a diagonal matrix with, on the right-hand side, this value. This matrix. Folks, this is our result. This is exactly our result. Now we got the missing matrix that is the inverse. This is I now, and this is P. We start with Q and I, we end with I and P. And you can go and then compute that it works. Let's see that it works. Here's the matrix, copied, 0, 0, 2, 1, 0, 0, 0, 1, minus 1. Like this, like that. What do we get? Four. Like this, like that? 6. Like this, like that? Yeah. This is the same as this. We went back in time. We developed the TARDIS. And now we can actually take any number of steps back. Any number of steps. Pretty cool, right? Pretty cool? Pretty cool. Okay. All right. Now, the question is, can we always invert a function? Because a linear function, can we always, okay, this is nonlinear, x squared. Can we invert x squared? 2 to the power of 2 is 4. I take the square root, I get 2. Right? Invertible. No. Because minus 2 to the power of 2 is also 4. I don't know. Was this one or this one? I don't know. You got a mapping of 2 solutions into 1. It's not invertible. I don't know. Okay, so that's not invertible. What about this one? Is it invertible? Only if A is not 0. And what about this one? Okay. Do you know what the red thing here? It's a little bit blood when I wanted to write. You know, so it just, like I have all these cuts now, so it dropped. It's a mistake from the past, remember? You don't remember mistakes from the past? Okay, here's a theorem, and here I'm going to finish. I'm going to show the theorem. We're not going to prove it. We're going to prove it next time. The matrix A is invertible if and only if the columns of A are linearly independent. Okay? If the columns of A are linearly independent, then the matrix A is invertible. Both sides. When you say invertible, A invertible means columns are linearly independent. If you say column linearly independent, it also means that there exists an inverse. That also means that if the columns of A are linearly dependent, then A to the minus 1, or the inverse of A, does not exist. There is no inverse. Okay? Very interesting. There's a proof for that. And the concept is we're going to assume linear dependence and invertibility, and then show that there is a contradiction. Okay? Then basically means the opposite. Okay? We'll do it next time. See you on, not tomorrow, no class. No class tomorrow. See you on Thursday.